For this lesson, we're going to be taking a look at derivatives of sine and cosine functions. This is as part of this chapter where we're kind of taking a look at the derivatives of functions that are not polynomials or rational functions, things that we've covered in the advanced functions course, exponentials, logarithmic functions, and now we're going on to trigonometric functions. So the first thing I want to do is I want to illustrate this idea, and I'm going to illustrate it using the same method that I used in previous lessons, which is I'm going to use GeoGebra. And in this case, I have a sine graph, and I'm going to use my GeoGebra demo here to just explore what happens to the slope of the tangent. So you can see I've got a point A here, and I've set up GeoGebra to allow me to move that point A anywhere along the sine curve. And now take a look. As I move through these various values, you see a shape starting to take place for B, and that shape describes, well, you should be able to piece that together. If we take a look at this red curve, then the slope of the sine curve is being represented as a cosine curve. And that actually tells us that the derivative of sine, because the derivative is essentially the slope of the tangent line, the derivative of sine is actually equal to cosine. So just like we did before, we can come up with expressions to describe the derivative of trigonometric functions. We did it with exponential and logarithmic functions. Now we're going to do that with trigonometric functions. And the derivative of sine of x is equal to cosine of x. And the derivative of cosine of x, it's not quite as simple. It's equal to the negative sine of x. You can show this graphically. You can just draw a simple sketch of sine, and you can actually figure out that it would become cosine. Same thing is true here. You can do a simple graph of cos and figure out that this is supposed to be negative sine. And taking it a little bit further, because we're not going to always be lucky enough to have it in this simple form, applying the chain rule here, y prime, and it's a very similar chain rule argument to what we did with logarithms and with exponentials. So first of all, I'm going to take the derivative of the overall function, which we know is cosine. So in this case, the derivative of sine is the cosine of the same argument. So that's going to be the cosine of g of x multiplied by the derivative of the argument itself, g prime of x. Similarly, if I take the derivative of cosine, the derivative of cosine is negative sine of the argument multiplied by the derivative of the argument itself. And this chain rule, in many ways, the chain rule is actually the rule of derivatives that we've used the most throughout this entire course once we started looking at derivatives. So let's take a look at some exercises, work through this. So in each case, I'm being asked to find the first derivative. Now, one thing, for this first one, I'm going to rewrite this in a form just to make you understand. Some people might look at this and think, oh, that's a quotient rule question. It's not actually, because this 5 over 2 is really just like a leading coefficient, 5 halves of sine of 4x. And so now when I take my derivative of that, y prime, the 5 halves just stays where it is. The derivative of sine is cosine. The argument stays the same. And then I multiply by the derivative of the argument, which is simply equal to 4. And then I've got some simplification that I can do here. 2 goes into 2 once, 2 goes into 4 twice, and I end up with 5 times 2 is 10, so that simplifies to 10 cosine of 4x. It's actually perfectly acceptable for you to write it this way without the brackets here, because this is a fairly standard convention in mathematics. The cosine of 4x, when it's grouped this way, it's understood that the 4x is the argument. But of course, if there's ever any ambiguity in what you're looking at, then you should use parentheses to make that part clear. For this one, I would actually recommend rewriting this one as the cosine to the negative 1. Actually, we need to be careful about that. It's not cosine to the negative 1, because that would be the inverse cosine. So instead, we should write this as cosine of 6x all to the negative 1. And so that way, when I take my derivative, I bring down the negative 1, so that becomes negative. Let's actually bring down the negative 1 itself. So that becomes negative 1 times the cosine of 6x to the negative 2. But now I have to take the derivative of what's inside here. And so now we're actually getting to the derivative of cosine itself. I need a little more room. The derivative of cosine is negative sine of 6x. But we're not done yet, because this one is a case of a chain rule inside a chain rule. I also have to take the derivative of this argument, which is equal to 6. So the negative 1 times the negative becomes a positive times 6. So in the numerator, I end up with 6 sine of 6x, all divided by this cosine of 6x goes to the denominator, cosine of 6x all squared. And I was going to make that mistake before with a negative 1, but we have to be careful because a negative 1 here means inverse. But I can put this squared here, and it's not going to lead to any confusion. And so that I would normally write as the cosine squared of 6x. Now you might notice a sine 6x over a cos 6x. Could we write that as tangent? Yes, we could. There's a number of different ways that we could write this, but this current form is perfectly fine for the answer we're looking for here. Until we knew what we were doing with this, if we were going further with this, then we might use some trig identities to change its form. But for the way it is right now, it could stay like this. I've got another couple of examples here, and so we'll do those next, but I'm going to move to a fresh page so that things aren't quite so crowded. So I've got that prepared already. The next one, I've got y is equal to the cosine of 1 plus x cubed. So for that one, relatively straightforward. We end up with y prime is equal to, so the first thing we run into here is we're going to take the derivative of the cosine. So we end up with the negative sine of the argument, 1 plus x cubed, multiplied by the derivative of that argument, which is 3x squared. And that is equal to negative 3x squared sine of 1 plus x cubed. And really, there's no need for us to go any further than that here. That's perfectly good. Now, this next one, I've got a quotient rule, and it doesn't look like I'm going to be able to get away from it. So I think I'm going to give myself a little bit more room. I'll bring this down here. And let's go ahead and start with the quotient rule. So y prime, I always take a look at these things and see if there's a better way that I could write them. But in this case, they're just a couple of linear trigonometric terms. There's not much I can do to simplify. There's actually nothing I can do to simplify here. So it's going to be the derivative of the numerator, which is going to be the derivative of sine is equal to cosine theta multiplied by the denominator, 1 plus cos theta, minus the numerator, which is sine theta, times the derivative of the denominator. And the derivative of 1 plus cos theta, well, the derivative of 1 is just 0. The derivative of cos theta is negative sine theta, all divided by the denominator squared. So 1 plus cos theta all squared. That is equal to. Now, in the numerator here, I immediately see I'm going to end up with a positive sine squared here. And if I multiply in my cosine, I'll get a cos squared. And that has me thinking of trig identities. So cos times 1 is just cos theta plus cos squared theta. And this negative and negative become another positive plus sine squared theta divided by 1 plus cosine theta all squared. And the reason I was pointing that out on the previous line is because you're not always going to necessarily want to expand every single thing that you see here. But if you have a good reason, as I did there, because what that's going to do is this part is going to be equal to 1 because of that's the Pythagorean identity. So using the Pythagorean identity, I can replace that with cosine theta plus 1 over 1 plus cosine theta all squared. And cos theta plus 1 is the same as 1 plus cos theta. So I can actually divide out this factor, divides out with one of those, and I end up with my final answer of 1 over 1 plus cosine theta. And then to finish off, I didn't even realize I had this extra example here. Again, I think I'm going to put this on a new page though. So let's go here and paste it. And make that a bit bigger. Okay, so now for this last one, we are going to, and first thing I'm going to do is point out to you this convention. So just to make sure that's completely clear, this is the sine of 2x, and that's the argument of sine. 2x is the argument of the cosine here. So what I have here is a product rule, but there's also going to be some chain rule going on here. So when I take my derivative, it's going to be the derivative of the first, which is, so the derivative of the first is cosine of 2x times 2 times the second, which is the cosine of 2x. So the derivative of sine 2x is this part times cos 2x plus the first, which is sine 2x, times the derivative of the second one, which is negative sine 2x times 2. And some simplifying, we're going to bring the 2 in front. Cos 2x times cos 2x is cos squared 2x. Now that's a lot of 2's together, so if you're not really careful about the way you do your exponents here, it might be a good idea to write this way instead. But the way I wrote it the first way is kind of the common way of doing it. It's a little bit quicker to do. I've got a positive and a negative and a 2 here, so that's going to become minus 2, and this one is going to be the sine squared of 2x. And at this point, this is fine the way it is right now, because again, unless you have a good reason to go further than this, I don't see why you would. But in this case, you might also recognize that I could take out a common factor of 2, which would give me a cos squared 2x minus a sine squared 2x. And you might recognize that as a trig identity, another trig identity. So now that 2 is in front, and this identity is 2 cos squared, and then sorry, I've just lost my train of thought there. Oh yeah, we could rewrite this as 2 cos squared 2x minus 1, or, so this could be or we could write this as 1 minus 2 sine squared of 2x. So we've got these alternate forms, and again, these are using the Pythagorean identity. And the other thing you might think of for this is, let's see, there's one more identity that you might recognize from this one, and that is that the cosine of 2 theta is cos squared theta minus sine squared theta. And it's also all of these other things. So all of these three all have something to do with this. And so another place I could take this one would be, again, I'm going to keep that 2 in front, and all three of these work backwards to here, which means this is the same as 2 cosine 2 theta, but I don't have 2 theta, I have 2x. So that's the cosine of 2 times 2x, which of course simplifies. The 2 multiplies in cosine of 4x. Now that might be useful, especially if you're doing something like you're solving or something along those lines. That might be particularly useful for you. Now, having done that, I also would like to point out to you, if we started all the way up here at the top, we could have recognized an identity here as well, which is there is an identity that sine 2 theta is equal to 2 sine theta cos theta. And I don't have 2 sine theta cos theta, I just have this part. So that would mean that I could replace this. I could have written this as y equals 1/2 sine of 4x. And then from here, I could have taken the derivative, and the derivative of that, if I go all the way down here, and all the way down here, let's go to y equals 1/2 times the sine of 4x, and I take the derivative of that, y prime is equal to 1/2. The derivative of sine 4x is equal to cos 4x times the chain rule tells me that's times 4. Then 4 over 2 is just equal to 2 cosine of 4x. And so had we converted that using our identity first, we would have actually ended up with a much simpler route to get to our derivative, at least to get to our derivative in this form. So I just wanted to point out to you there that there are different paths that we can take, and they can be valid but useful in their own different ways. And finally, I think we're going to wrap up with this example. And so the question asks, given we want to find the slope of the tangent to the curve, so we're given the curve here, and we want to find it at this particular point. So the first thing we need to do is figure out what is our derivative. Y prime is equal to, so first I've got a power rule. I'm going to bring the 2 down in front. Sine x minus cos x to the power. Normally I wouldn't write this. We brought the 2 down. This whole thing is now to the power 1. But now I have to chain rule this. I have to take the derivative of the argument here, which is sine x minus cos x. And the derivative of that is going to be cos x. And this is minus a minus. The derivative of cos x is negative sine. So I've got a minus becomes plus sine x. And from this point, we can go ahead and substitute our values in here right away, or we could recognize that we've got a difference of squares here, and so we could write this out as sine squared minus cos squared. There's different things we could do there. Let's just go ahead with the kind of the most direct way, which is we've got x is equal to 5 pi by 4. So what I'm going to do is 5 pi by 4, so we've got 0, pi over 2, pi, 3 pi by 2, and 5 pi by 4 would be down here. And we've got cast. And so we know for 5 pi by 4, our related acute angle is here at pi by 4. And so when we're going to be calculating the sine of 5 pi by 4, but the sine of 5 pi by 4 is the same as the negative sine of pi by 4. And the sine of pi by 4, if you remember your special triangles, that's going to be negative root 2 over 2. Similarly, the cosine of 5 pi by 4 is equal to negative root 2 over 2. So now that I've got those two values, I can just go ahead and substitute them in. So Let's leave myself enough room to write this, but still see our original expression. At x equal 5 pi by 4, y prime is equal to 2. And now the sine of 5 pi by 4 is negative root 2 over 2. And this is going to be minus the cosine, which is also negative root 2 over 2. And then the second bracket is cos plus sine. So that's going to be negative root 2 over 2. And this one's going to be plus a negative, which is just minus. Actually, let's go ahead and write it. We'll just say plus negative root 2 over 2. That doesn't look quite like a negative there. And so y prime is equal to 2. And now in this bracket, I have negative root 2 over 2 plus root 2 over 2, which actually works out to be 0. And in this bracket, I have negative 2 root 2 over 2. Because there are two of them, they have the same sign. But of course, it doesn't end up mattering because of this 0. So we end up with an overall value of 0. So therefore, let's just see, what did the question want? Wanted the slope of the tangent line. Therefore, the slope of the tangent line at x equal 5 pi by 4 is 0, which is what we found right here. And that is it for this lesson. There are some exercises to explore. We're looking right now at sine and cosine. We'll be looking at tangent in an upcoming lesson.